I'm not going to screen share yet because what I have open is homework 1, which is just the Word document. So you can open that up on your own screens and look at it. There's nothing that we need to refer to together. That way we can continue to see each other and keep this experience as normal as possible. Let me double check that my recording appears to be working. Looks like it can. Somebody talk to me again so I can check the recording audio, please.
Is it working?
Yes,
Can you hear me?
I can hear you, and the green bar moved over, so I feel like that's a positive sign. Excellent. All right, so then we have the remainder of homework 1 to talk about. We have lecture 3 to start, and potentially the second half of example 2 on tap for today. So welcome back, everybody. I have homework 1 open here, and I have number 5 as the next thing that we have to talk about, unless there was anything from questions 1 through 4 that folks wanted to ask about before we dive back in. No? All good? Good enough anyway? All right, cool. Number 5 then says, how does one fit the univariate and multivariate variants of repeated measures ANOVA as multi-level models? I.e., what goes into each side of the model to do so? And then what are the limitations of doing this? So first question then, univariate and multivariate repeated measures ANOVA. What goes into the model for the means with respect to the fixed effects? If I wanted to do an analysis of variance on time, for instance, I have a longitudinal study and I just want to do an ANOVA. What am I doing when I say I'm going to do an ANOVA? Categorical time, yes indeed. You can talk or type, up to you. What does it mean if you say categorical time?
Yeah, we must include time as a categorical predictor. We use it as a discrete variable, and basically we are trying to perform a saturated time model, right?
Mm-hmm. Yeah, the key idea is that you're estimating as many fixed effects as you have distinct occasions. And you can set that up in a traditional way where one of the occasions is the reference and the fixed slopes tell you about how different each other occasion is from the reference. Alternatively, you can kick the general intercept out of the model, in which case each of the slopes actually becomes an intercept that denotes that occasion versus just 0. Either of those would work the same way, just a different parameterization. So in terms of limitations, we have direct message already answered the question, but what are the limitations then of having to treat time as a discrete variable? When would that become a problem?
Compound symmetry.
Oh, that's not this one. Hold that thought though.
I think because I joined my
Just a second.
screen here, so okay, I take it back.
No, you're right. You're just answering the next question.
Oh, okay.
Balance time to be able to do that.
Yep, balance time. Yep, because if you have to have a separate fixed effect for every occasion, then you're assuming that everybody's on the same schedule and there's only so many occasions. So you would have to round people into the nearest occasion in order to fit an ANOVA model, which is a saturated means model. On the variance side, what goes into the univariate version versus the multivariate version? And now you can say your answer, Nathan.
Compound symmetry.
Yeah, which one is that? Univariate or multivariate?
For univariate.
That's univariate. So the idea of having a random intercept only then allows us to separate out that variance and not include it in the error term in testing any differences with respect to time. That assumes what about change over time though, if we have a random intercept only, compound symmetry? Yeah, everybody changes the same. So it doesn't have to be linear. It's whatever pattern of mean differences you have across occasions is assumed to hold for everybody. In other words, people only have different intercepts, not different slopes or different time differences of any kind. And so then the alternative is multivariate, which is known by a couple different other words. What does a multivariate approach to repeated measures have in the model for the variance?
Unstructured.
Yeah, unstructured. Give me another word that means that.
brain is going to.
Okay, people who had SEM last year, saturated. The H1 or the HO model?
H1.
H1, remember you are always the hoe. We'll talk about that later. H1, yeah. So what happens with respect to the model parameters if you fit this unstructured or saturated H1 model? What are you fitting? More of a description than a prediction, correct? A cornucopia of parameters. I'm going to translate cornucopia into a separate variance for each occasion and a separate covariance for each pair of occasions, which means a whole lot of parameters. It still requires balanced data to have a separate variance per occasion. You can't have intermediate possibilities. And in terms of limitations, folks have already put into the chat the big one, complete data. That's the big one. So the problem is not the ANOVA model per se. The problem is the use of ordinary least squares estimation to get the model parameters. You can't have missing observations because then your sum of squares isn't really a sum and you can't get anything else. So you can have incomplete occasions. You can keep whatever occasions you do have, I say incomplete people, if you switch to some kind of likelihood estimation. And the same is true if you use Bayesian estimation, which is likelihood plus a combination of prior distributions. So there's nothing wrong with ANOVA per se. If it fits, you have complete data and it's balanced data. It does have another limitation in terms of what kind of predictors. Yes, that was where I was going to go next. You can have time invariant predictors, but you can't have time varying predictors. Invariant predictors would be an ANCOVA, where the C stands for covariate, which means a person level predictor, usually a quantitative predictor, but it doesn't have to be. Good. Other things I'm forgetting that you wrote down about number 5. Feeling good about that? Cool. Number 6. What is the difference between alternative covariance structure models that only use the R matrix versus those that use G and R? So first off, what do those letters mean? G is an abbreviation for what in these models? What goes in the G matrix?
Random slope.
Random variance, yeah. So G is random effect variances and covariances. So if you have an intercept, a slope, and any covariance, the variances of those terms go in G. So those are level 2 between person variances. Cough, cough, homework question. If I have a random slope, that is between person variance in within person change. It's the way that I would say it. The slope for time is a within person slope. If I let that time slope differ across people, I have between person variance and within person change. In these models, though, we don't typically have a random slope. We might have a random intercept. So what is R then? What goes in the R matrix?
So I know it's not residual variance because that's the thing that I feel like I said that last semester and I was wrong, but it has something to do with within person variance.
It does. I would call it residual variance, actually.
Oh, you would?
I would.
Okay.
So the question is, what all is in R depends on whether G is involved. Yeah, so if you have only R, then all the variance and covariance is in one matrix, and so I would call it total or marginal. There's no separation of what's within and what's between. Everything's in R. If you add the G matrix, then what's left in R after taking the G part out, after taking the random effect variances and covariances out, R becomes just within person residual. So the variance and covariance of the E's across time is what R refers to. So then the question was, what is the advantage of having this G and R split into between versus within? Simpler. When there's a high intra-class correlation, yes. Yes, that's where I'm going.
And we can also save some degrees of freedom.
Yep.
Most of the time, maybe the main reason for people differing to each other is because they have constant difference in the intercept, right?
Yeah, there is often in data with people, at least, I will say in the social sciences, there's almost always some degree of correlation between every pair of occasions, no matter how far apart they are in time. Like because they come from the same person, there's usually a very substantial intra-class correlation. So anticipating that and allowing a baseline of, okay, I'm just going to let all of the occasions have some degree of correlation. It's going to be the same correlation. That's my random intercept. Then the question is, are residuals from distant occasions still correlated? Extra? And usually the answer is not very much. So like occasions that are 1 unit in time apart, maybe 2 units, maybe 3, you might need some kind of residual correlation for that. But you don't have to have like a lag 7, lag 8, lag 9 residual correlation because the random intercept is probably going to take care of that. So the logic then is the resulting R matrix can be simpler, can use fewer parameters, spend fewer degrees of freedom, and when put back together again, they can still do just as good of a job. That's my answer. It's also useful from a, how do I want to say this? Explanation point of view to be able to talk about how much of the variability is due to cross-sectional differences, mean differences versus time differences, and to be able to have those variance components estimated separately and watch how they change as you build the model. So I feel like that's a useful thing just to convey what you're doing and the impact that it has. It's harder to see the impact of that when everything is shoved together in one R matrix. Okay. Any questions on that or parts of that that you want to hear again? I'm trying to talk a little slower just in case I'm on a lag. Question?
I have one. Yes. So if we use only the R metrics, we are assuming that variance between people is the same, or there is no variation between people.
You're not assuming anything about the between person variance per se if you only use an R matrix because there's no distinction of that kind. So,
Right.
like for instance, an AR1 pattern to an R matrix would say that the total variance is the same across time on the diagonal, and the lag correlations are the same for the same distance in time. So lag 1 is this related, lag 2 is R squared, lag 3 is R to the third, etc. There's no utility in talking about between versus within because that's not how the model is structured. It's structured to just directly replicate the total variability and the total covariability over time.
Thank you.
Good.
So another question. I just want to make sure. So our only matrices, do they assume constant variance and covariance across occasions, or no?
Not necessarily. I would say that, so there's only, at least the way they're built into software, let me put it that way. The choices that you have for R matrices in traditional univariate MLM software come in 2 flavors. Either the variance is homogeneous or the variance is heterogeneous. And there's no, yeah, and so it's a likelihood ratio test to see if they need to be heterogeneous. But there's no intermediate possibility by which they can be heterogeneous but not estimate a separate one per occasion. That's what the random slope models allow, is heterogeneity that is as a continuous function rather than this one, this one, this one, this one, this one. All right, other questions? Thanks for talking, folks. I appreciate it. I know it can be a little intimidating to put yourself out there, and I appreciate it. And the folks at home do too. They get tired of listening to me.
I have a question.
Mhm.
Do you have like an easy way though that you remember G and R? Because R makes me think random. I don't know. I just like can't keep them straight, and it seems like they just like put letters to them.
They did.
So,
So this notation system is coming straight out of the SAS proc mix documentation. Other people will substitute the letter T for the letter G. R is almost always R. So it's somewhat arbitrary, but we have to have a name for things to be able to hold the idea. The R to me stands for residual. And maybe you could think of it as, why do they call level 2 G? G, I don't know, that's so random.
I like that. That's perfect. Thank you.
Gee, that is so random.
Like the hoe. I just needed someone like I'm the hoe. So.
Yes. That's what I do anyway. I always think of it like, also here's another one, Guns N' Roses from the 1980s and 90s. It was called G and R, and G always comes first, right? Like level 2 comes first, level 1 comes second. So there's another one. Welcome to the jungle, folks. That's what I can say. All right. More vocabulary then. Let's add some more letters to our list. Question 7. What's in Z? We did G and R already, and V. How do these things relate to each other?
Is V just G and R combined?
Yes. Not added, because there's Z gets in the process of the combination, but yes, you can conceptually think of it as V is G and R put together.
And then Z is like what you do to make that happen.
Yes. Z is what you do to make that happen.
Yeah.
So V, I would call that put together again. Marginal would be the right term for it, like technically. Total. It is when you put all of the model for the variance back together again, this is describing what is being predicted for the covariances and variances across time. Z, can I say, Z is the indicator matrix of the time-dependent variable. It can mark the relative location of each occasion in a longitudinal study. Very close. Z, I would say Z is an indicator matrix. It holds the values of the predictors to be given random effects. So if you are including a random intercept in your model, then Z holds a column of ones, and it holds as many ones as you have occasions. And since it's just an intercept, they're all ones. There can only be ones. If you add a random slope of a level 1 time varying predictor, Z holds the specific values for you of that time predictor. So if you showed up on time and you went to all the occasions, you might have 0, 1, 2, 3, 4, 5. Someone else who missed the last couple of occasions just might have 0, 1, 2, 3. Somebody who showed up in between might have 0, 1.5, 2.5, something like that. So you're both correct. I think Lily said that the idea that Z wraps around G to make it fit back together. Yes, that is true. But the other purpose that it serves is this idea of applying the variance components to your specific set of occasions. And Z is the matrix that holds that information about which occasions you have, and thus how the model variance components work together to create like what would be predicted for you. So putting in terms of what's common and what's shared, Z is individual specific. If everybody is on the same balanced time schedule, then Z doesn't have to be individual specific. The same Z would hold for everybody. If everybody is has complete data and is on balance time, then it would literally be the same Z for everybody. Otherwise, Z would have the same values, but potentially have missing rows for people with missing data. G is the level 2 matrix of random effect variances and covariances. That's for everybody. There's only one G, unless you tell the model otherwise. But in everything we've seen up to this point, there's only one G. Likewise, there's only one R. So whatever structure you put into R, whether there's different variances at each occasion's residuals, different covariances, any covariances, those are assumed to be shared. So V, when it's put back together again, is individual specific because of the effect of Z, which is the individual predictors to be given random effects. Okay. So if there are no random effects, then V equals R. Yes, it does. And I think that's where some of the differences in confusion and notation gets to be, is like V is R, and so in some people's writing, like they'll confuse something where they mean Z, V, they'll say R because it sometimes just is R. So try to recap. V is put back together again. If there's nothing to put back together again, then it's just R. Otherwise, it's R and G put together again. Welcome to the jungle. Okay, how we doing?
Good. I have another question.
Hit me.
Related to G. Does it also serve the function of like aligning the dimensions of R and G?
Yes.
Okay.
Yes. So it wraps around G so that G becomes the right dimensions to be added to R to make V. Wraps around is my way of saying pre and post multiplies, because that's like what it looks like around on the equation. Is it incorrect to say Z matrix is dichotomous or binary? Probably I would say, because it doesn't always have to be. It would be ones only if there were only a random intercept, but if there were other random slopes, then the values would be whatever the person has for the predictor that's been given the random slope. There are zeros for the cross person columns though. So in that sense, I can see why you would say binary, but I'd say it's not always binary, just sometimes if there's only a random intercept. Cool. Okay, is this helpful to go over some of this stuff and words and concepts? Good. I did it because like we all need a review, but we also need to kind of get on the same page with respect to terminology. And the way that I talk about things is not the same way that everyone else talks about things or writes about things. And it can become very confusing when you're trying to translate across sources. So, all right, number 8, then we're moving right along. How is dependency of residuals captured by adding random effects? So dependency, what does that word mean, first off? Covariance, correlation. Yep. If people say, oh, you have dependent data, what they mean is that you have a sampling design in which the residuals of certain cases are likely to be correlated with residuals of other cases because of the sampling. Occasions from the same person. If I have a more intensive longitudinal design, let's say I have multiple occasions in a day over multiple days, then occasions from the same person are certainly going to be related, but beyond that, occasions from the same day within the same person are going to be more related than occasions from different days. So that's another layer or level of dependency that we would have to build into the model. So how do random effects then address dependency, is the question. What's the relationship between adding random intercepts versus random slopes and what that says about your dependency, your correlation pattern? Ooh, no one wants to take this one. Should I answer it? You know, you can type to me and use the DM feature if you're feeling shy.
I can get us started.
Please.
So what I have so far is like random effects allow individuals to differ from like the overall sample mean if that's what we're estimating. And so some individuals may be consistently higher, like all of their occasions are consistently higher than the mean or
Mhm.
lower than the grand mean. And so the random intercept would allow folks to differ and essentially like why are you different than the mean because why are you off of the correlation?
Yes, that is all true. What kind of correlation pattern in the residuals does allowing a random intercept then induce into the prediction? If I only have a random intercept, what pattern of correlation am I saying that I have in the occasions from the same person? Not quadratic yet. Constant, yes. Constant mean differences translates into a constant correlation pattern. All of the residuals from the same person are equally correlated regardless of when they were measured. Constant. So you are allowing each person to have their own like deviation in the mean. That is inducing a correlation in the residuals, but it's inducing a correlation for a reason, mean differences, and of a particular pattern, which is constant. If I add a random slope to the mix, then I am doing two things. I am introducing a pattern of variance heterogeneity over time that is quadratic. I wouldn't necessarily count that as dependency though, because what you're doing is allowing the variance to change. But in doing that, you're also allowing the covariance to change as a function of which occasion it is. There's a complex function that's in the formulas, but basically what it does is start with the intercept variance as the basis for the correlation between any two occasions, and then add pieces to that that are time specific that multiply either the random intercept and slope covariance or the random slope variance. So it's non-constant is the point. I don't need you to memorize the formulas. But each random effect that you add is introducing a different pattern of heterogeneity of variance and a different pattern of residual correlation. So the random effects are the reason why occasions from the same person were correlated, such that after you include them, you can have an R matrix that has no correlations in it. The residuals would be independent if not for the random effects. If that's not true, then you need to add something to the R matrix that allows some kind of additional time-specific correlation. Does that make sense? Maybe? Okay, random effects induce correlation. The kind of random effect it is changes what the correlation is. You can always tell if you're headed in the right direction with some kind of likelihood ratio test, AIC and BIC. There may not be an answer key to come back to if you don't have balanced data, but you can always add random effects and see if it helps. The other half of the question, can random effects explain variance in an outcome? According to me.
No,
No.
because they don't tell us why the variance is there.
Yes.
So we can say that it accounts for some of the variance or that it partitions the variance, but it doesn't tell us why, so it can't explain it.
Yes. And I will die on that hill. So your level of indignation with the no is correct to me. A random intercept is an error term, still. A random slope is an error term. We can estimate variance of those error terms and say how much of the variance is because people have mean differences and how much is because they have slope differences, but we don't know why those differences are there. That's why it's not an explanation. I like the words, attribute, it's attributable to, or it's due to, or something like that, that recognizes it's a component, but it's not an explanation. And the reason that I have to clarify that it is to me is because there is a subset of people who routinely compute R-square values that involve random effects. And those are called conditional R-square values rather than marginal, which is the version that you've seen from me. And to me, that just theoretically does not make sense. So given that there is controversy, if you ever give any kind of R-square measure as an explanation of variance effect size, be very clear about how you computed it. That way people can agree with you or disagree with you about how you computed it, but at least they'll know. In multi-level models, there's like 8,000 kinds of R-squares that have been published. And a lot of them overlap, and they're all called different things. So, okay.
Can I ask a question, please?
Please.
Is there a way we can tie this down to what we have in the V matrix, given that if we don't have a random slope, what we have in the V matrix, and when we have a random slope, when we sum what we have in the R and G matrix together, it's going to be the same as what we have if we had not added a random component to the model.
Okay, I think I understood the question. Let me try to answer it, and you can tell me if you meant that or something else. What V looks like if you only have a random intercept is on the diagonal, the total variance at each occasion is partly due to the level 2 intercept variance and partly due to the level 1 residual. So it's like the U0 variance plus the E variance goes all the way down the diagonal in V. The off diagonal in V, which is the marginal covariance between occasions, is just the random intercept variance. That's compound symmetry. And it's the same across the whole off diagonal. When you introduce a random slope, then the diagonal is going to be a quadratic function that has time squared in it. It has the intercept variance still, and it has the covariance, I believe, in there too. So it's not as easy to summarize because it has basically a 3-piece function that depends on which occasion it is. And the same is true for the covariances. It depends on which pair of occasions you're talking about. Was that the question that you asked, or did I just make that up?
Yeah, I think it is. Yeah, thank you.
Okay. Cool. What else? Are we ready to move on to the next one? Yeah, all right. What is the purpose of including fixed and random effects related to change over time? So what kind of research question, or what is the goal? Let's say if you add fixed effects of time, what are you trying to do or capture?
The fixed effect, I think, is to describe the average pattern.
That's exactly it. Fixed effects describe the average trajectory, aggregating across people. So whether it's linear, quadratic, piecewise, exponential, logistic, whatever it is, you're trying to describe what happens on average. Then what is the purpose of including random effects? What do they do?
Reflect kind of individual deviations or differences relative to the fixed effect.
Yep, everybody gets their own if you're adding a random effect. Individual specific deviations from the fixed effects. And because they're phrased as deviations, which comes first? Fixed or random? Always fixed. Yep. Because the fixed effect is the center of the random effect distribution. So it is okay to have a fixed effect that doesn't have a random effect with it. That just means everybody gets the same. It's not okay to have a random effect without the corresponding fixed effect. So random effects conceptually are allowing individual differences in intercepts and in parameters related to change over time. Behind the scenes, they're also helping to capture person dependency that is due to particular patterns. Constant dependency captured by a random intercept, non-constant dependency captured by random slopes. Yeah, that was an easy one, I think, relatively speaking. But it's important not to lose like the forest, right? Like, what are these things for? Last but not least, number 10. What are the roles of time invariant predictors in the model for the means, and how do they relate to which source of variance they explain? So if I put a time invariant predictor into the model, a level 2 person characteristic, something that's constant to a person over time, what am I doing? What am I hoping to achieve? Tenure! No. If I put in a main effect, let's say that I have something like education level, some background characteristic they come in, and I put in a main effect of education. What is that main effect of that time invariant predictor doing in my model? Yeah, adjust the growth curve or moderate the growth curve. So if I have a main effect, which part of the growth curve is being moderated or adjusted? If I have a main effect, intercept, yes. Adding an intercept, or adding a main effect of a level 2 predictor adjusts the intercept up or down. Because it's a level 2 predictor, it's the intercept for the whole person's data. Like it would shift their growth line like all the way up or all the way down by a constant amount. Because it's a person characteristic, it would apply to all of their occasions. If I'm adjusting the intercept by a level 2 predictor, then which type of variance should be reduced as a function of having introduced that predictor? Level 2, but more specifically,
Random intercept variance.
yeah, the intercept variance that goes with it. There's a direct correspondence there. If you introduce a main effect of a time invariant predictor, you are seeing whether it moves everyone's intercepts up or down. If it does, then the U0 variance that you have should shrink relative to what you had before, because that intercept has been partially explained by the time invariant predictor. And here I do think you can use the word explain, because you have a predictor that is a separate variable in your data set. And presumably you have some sort of theoretical reason for putting it there. If I have what's known as a cross-level interaction, so if I have something like education by time, what is its job?
I'm sorry, can you repeat the question? I was typing.
No problem. So the next one then, if I have an interaction between a time invariant level 2 predictor like education with a time varying level 1 predictor like time, so education by time for instance, what is its purpose? What is it trying to moderate? Level 1, yes. More specifically, if I have education by time, for instance. No cohorts today. I'm trying to keep it more straightforward. Although the same is true, though. Cohort by time is what we're would be another example. Yeah, the time slope. So you are trying to moderate the effect of the predictor that is involved in the interaction. So if it's education by time, I'm saying the time slope varies by education. If it's cohort by time, the time slope varies by cohort. If it is education by time squared, then the quadratic part of it varies by education. The amount of curvature or acceleration varies by education. So it's a specific pattern of moderation for that term that contributes to the growth curve. That means then which kind of variance should that education by time example of a cross-level interaction explain? It depends. Ah, you caught me. You're right. I was trying to trick y'all. It's tricky. That's the theme for this semester. It is tricky. Now, why does it depend? Why isn't there just an answer? What does it depend on?
It depends on if that level 1 variable has a random slope or not.
Yes. If it
We
does,
have a,
then what?
so we will be explaining random slope variance. If we do not have a random effect for that level 1 predictor, we will be explaining residual variance.
That's right. If the level 1 predictor has a random slope, the interaction of level 2 by level 1 explains that random slope. So if I have a random effect of time in my model, education by time should reduce that random time slope variance specifically. If I have a random effect of time squared, if I have a random quadratic, then education by time squared should reduce that quadratic slope variance. So it's a specific one-to-one match. Now, if that variance isn't in the model, like if I have a fixed quadratic slope for time and I don't have a random slope variance with it, then it has to explain residual variance instead because there's nothing left. In practice, these things are never neat and orderly. You can see the variance components fluctuate across models even if they're not supposed to, and that can cause the R squares to go up or down. Like they can go, like the variance can get higher, which means the R square would be negative. And that's why alternative ways of computing changes R squares that do not use different models but try to use the same model can be more useful. Last semester I gave you a couple readings about that topic towards the end of the semester. So it can get tricky, as if everything else. What about an interaction of two level 2 predictors, like cohort by education? What would they be moderating?
Would that be the intercept?
Still the intercept. What about cohort by gender by education by whatever? Same, intercept. So it's only going to moderate a slope if it's interacting with a variable that has a level 1 slope. So a cross level interaction. If they're both level 2s, then it's the intercept. Good. All right, I think we finished it. So if you're taking notes along with us, I'm going to give you a second or two to look down your page and see if there's anything that you want me to say again or differently that you can help feel good about. Turn in your answers for the effort draft, I think due like in a week and a half. That sound right? No? We're feeling good about this?
Wait,
Yes?
sorry, semantics, but you meant accuracy draft?
Yeah,
Right?
I did. Sorry. Yes, the one that I'm going to read and give you feedback on and a grade. The first draft was to make you think enough about these questions to have an answer ready when I call on you. Like to realize like what you need to review, right? Because if you can't answer the question off the top of your head, then you need to go back over. So that was the intent of the effort draft, was to encourage the beginning of the review process. But the accuracy draft then will be due whenever it says on the syllabus. I haven't moved that. I think it's about 10 days, but I could be wrong. Okay, going once, going twice, sold. We're done with this one.
Yeah, sorry, but I have one. I didn't want to say anything, but then I will regret. So, could you please explain in one sentence question A, the first part, how is the tendency of residuals captured by adding random effects? Because you said many things, but could you try to summarize this in one sentence?
I can try.
Thank you.
Random effects introduce correlation between residuals for reasons. And the reasons correspond to different patterns. So if the residuals are correlated only because some people are just higher all the time, then there should be just a constant correlation, and a random intercept creates a predicted constant correlation. If people change differently from each other, then the correlation has to change over time as well. And a random slope would introduce a non-constant pattern of correlation over time. How's that? There's not a single set of right answers for a lot of these. Like, I'm looking for you to try and put it in your own words and the way that you're processing this, because that is, I think, a useful thing to try to do, even if, it's just for a homework or whatever, but to be able to vocalize these things. So does that help you enough? You feel good about that?
Yeah, to me, the main idea here would be something like, we have some specific data characteristics that we are trying to capture via random effect, and we use random effect, we are introducing a specific pattern for between the studios. That works?
I think that works.
Great. That's all what I need. Thank you.
Sure. All right, then what I'm pulling up next, changing gears. Actually, let me stop the recording, because then I can have a clean segue